Hello everyone and welcome to this new video on Module 6. In this module we will dive into the software testing process. We will start by understanding what software testing is and explore the important difference between verification and validation. After that we will learn about the different stages of testing. This include development testing, release testing, and user testing. Finally, we will wrap things up with a review question to help us reflect on what we have learned and solidify our understanding. So let's get started. I will start as usual with my first question, which is what is software testing? Software testing is not just about making sure a program functions correctly, it's about ensuring it meets specific requirements and identifying any defect before the software is put to use. This involves running the software with artificial data and examining the results for errors and anomalies. The second question that I have for you is why do we need the process of software testing? Or why software testing is important? Firstly, it demonstrates that the software meets its requirements and work as expected in normal usage scenarios. For example, a banking application should handle valid transactions correctly, like processing accurate deposits and withdrawals. Secondly, it creates complex test scenarios to uncover hidden issues, such as system crashes, incorrect computations, or data corruptions. For example, the same banking application might be tested with invalid transactions amount, unusual account numbers, or hundreds of simultaneous users to see if it can handle this situation without failure. Both aspects are important to deliver a product that's not only functional but also reliable. It's common to call the first goal validation testing, ensuring the software meets user requirements, and the second goal defect testing, which focusing on uncovering flaws in the system. In the following slide, I will show you a figure that explains the difference between validation testing and defect testing in more details. We start with a set for the input data that we have, which is passed into the system we want to test. Here we treat the system as a black box, meaning we don't concern ourselves with how it works internally. Instead, we focus on the output generated by the given inputs. In the validation testing, we are concerned with the outputs of the system under normal usage scenarios. For example, if we are testing a calculator application, we could test it with standard inputs like multiplying two numbers, dividing two numbers like 4 by 2, and the expected output should be, of course, 2. Now let's consider a subset of the input dataset that will lead to an error. I will call it IE, the input that will cause an error. When I pass this input to the system, I expect that the output will not be correct. And this is a subset of the output of the system too. Here we are talking about the defect testing, which focus on a subset of input data that could cause an error or unexpected result. For example, instead of calculating 4 by 2 in the calculator application, we could test 4 by 0 to see if the system handles the error appropriately or not. Similarly, we could input an extremely large number to see how the application processes. I encourage you to pause the video for a moment and think about what kinds of defect testing you would conduct if you were testing a program. I'm talking in general here. I mean, it could be a calculator application, like I mentioned, or any kind of application. For example, I mentioned dividing by 0. What else can you think of? A few examples that came to my mind is If a form field, expect a phone number. Try entering alphabetic characters or special symbols. For a date field, test an invalid date like February 30. If test box only allow values between 0 and 100, try entering 101 or 102 or 200 or a negative number to see if the system will reject it or not. If an application only allow uploading a JPEG file, try to upload an exe file or any different format file and see how it will respond. Submit a form without filling out the mandatory field, or rapidly click a button multiple times to see if it will cause the system to crash or behave in an unpredicted way. These are just a few examples, and I'm sure you can think of more. I would love for you to share the examples you came up with, especially if they weren't mentioned here. Finally, I want to emphasize an important point. There is no strict boundary between validation and defect testing. During validation testing, you may still uncover defects in the system. Similarly, during the defect testing, some tests may show that the program meets its requirements. Let's take a closer look at two key concepts in software testing, which are verification and validation. Verification ensures that the software is built according to its requirements and specifications. It answers the question, did we build the system right? This is all about checking whether the software functions as it should based on the design and technical requirements. Validation, on the other hand, confirms that the software aligns with the customer's expectations and needs. It answers the question, did we build the right system? Here we focus on whether the software delivers the intended value to its users or not. Again, think about I'm asking you to build a program to calculate the factorial. And instead calculating the factorial, you are calculating the Fibonacci number or Fibonacci sequence. You build it correctly, but it's not the right system. You build the system other than that I'm requiring. The ultimate goal of both verification and validation is to ensure that the software is suitable for its intended purpose. However, the level of confidence we require in a system can vary, and it often depends on three main factors. The first one is the software purpose. Software that is critical, like safety systems in a car or medical devices, requires extremely high reliability. On the other hand, a prototype showcasing a new product idea doesn't need the same level of strictness or precision. The second level is the user expectation. When software is first launched, user might overlook some bugs, especially if it provides a useful features or benefits. However, as time goes on, they expect the software to work more reliably, which means through testing it needs to work as perfect as they can. Another thing, if the product is for free for the customers, they will not have the same expectation when they pay tons of money, to get this product. And finally, the market condition. In competitive markets, companies might release software quickly to stay ahead, even if it hasn't been fully tested. Similarly, if the software is sold at a lower price, users may be more forgiving for occasional issues. In this slide, we are comparing two important processes in software verification and validation, which are inspection and testing. So, what is the difference between inspection and testing? Inspection is a static analysis technique. This means it involves manually examining the source code, documentation, or related material without actually executing the software. For example, during an inspection, you might review requirement specification or diagrams to ensure everything aligns with the intended design and functionality. Testing, on the other hand, is a dynamic process. It requires running the software with various input values to verify whether the outputs are as expected. For example, testing often involves interacting directly with a program to identify defects or confirm correct behavior. As you can see in this figure, there are different software components, such as requirement specification, software architecture, UML design models, database schema, and finally a program that can be executed. Now, if we consider both processes, inspection and testing, you will note that inspection, since it doesn't require running a program, can be applied at all stages. This means you can inspect the requirement specification, the software architecture, the UML design model, the database schema, and even the program itself. However, testing is usually limited to the later stages when the system or program is ready to be executed. Of course, there are exceptions. For example, testing can sometimes be involved in the requirement specification stage. Think about this for a moment. When could this happen? It could happen when we are building a system prototype. In this case, the testing process can be involved since there is a functional program that we can test or we can evaluate. Now let's discuss the advantages and the disadvantages of the inspection process. As usual, I encourage you to pause the video for a moment and think about both the strengths and limitations of this process. Let's start with the disadvantages. Time consuming. This inspection process can take a significant amount of time since it requires detailed manual reviews. Dependence on expertise of the reviewers. The effectiveness of inspection depends heavily on the skills and experience of the reviewers, which makes sense. Human errors. Being a manual process, it is subject to human error, where reviewers might overlook certain defects or whatever. And another thing that I'm thinking about right now, inspection cannot verify non-functional requirements like performance, usability. For example, while an inspection can ensure the correctness of a database schema, it cannot assess how fast the database queries will run or how user-friendly the interface is. Now, moving on the advantages. Avoiding error overlap. Unlike testing, inspection don't involve running the software, so one error won't hide another. This makes it easier to find multiple problems in a single session or single iteration. Low cost for unfinished systems. Inspection can be done on unfinished version of system without extra costs, unlike testing, which might need special setups or environment to test incomplete programs. And finally, finding programs early. Inspection help catch issues early in the development process, often before the software is run. So fixing problem early saves a lot of time and effort later on. It is important to note that inspections and testing complete each other. They are not opposing techniques, but work together as part of the verification and validation process. So both processes are essential for ensuring high quality software and should be used together during the verification and validation process. In the traditional software testing process, we begin with designing phase of the test cases. The result of this step is a set of test cases that include the input specifications and the expected output from the system. These test cases, along with a clear statement of what is being tested, serve as the input of the next stage, which is prepare test data. The prepare test data stage is responsible for creating the actual test inputs needed for the following phase, which is run program with test data. In this phase, the program is executed using the prepared test data, and the system generates its actual output based on the provided inputs. This output is then passed to the final stage, which is compare results to test cases. At this stage, the actual output is compared with the expected output specified in the test cases, and the result of this comparison is the test report, which is the final output of the entire testing process. Now let's discuss the three main stages of testing that a commercial software system typically goes through. The first stage is development testing. This happens during the creation of the system and is aimed at finding bugs as early as possible. In this phase, designers and programmers are involved, testing their work as they build the system. This helps ensure that any issue are identified and resolved before moving to the next stage. The second stage is release testing. This is carried out by a separate testing team independent of the developers. The goal here is to verify that the system meets the requirements of the stakeholders before it is officially released. This stage provides an additional layer of assurance by testing the system from a fresh perspective. The final stage is user testing. In this phase, actual or potential users test the system in their own environments. This includes acceptance testing, where the customer evaluates whether the system meets their standards and expectations or if further refinements are needed. Each of these stages plays a critical role in ensuring the software is reliable, functional, and ready for use. Let's explore these stages in more details. Let's dive into the first stage of testing, which is development testing. This includes all the testing activities that are carried out by the development team as they build the system. Development testing is an important step to ensure that the software is free from defects before moving on to the next stage. There are three main types of testing within this phase. The first one is the unit testing. This focuses on testing individual programs units or object classes. The goal here is to ensure that each object or method work as intended. For example, if you are testing a function that calculates the total price in a shopping cart, unit testing would check if it correctly adds the item prices together or not. Then component testing. Once individual units are working correctly, they are combined to form a larger composite components. Component testing focuses on testing the interface between these units to ensure they work together properly. For instance, in a shopping cart, this might involve testing how the prices function interact with checkout process, for example. And finally, system testing. In this step, some or all the components are integrated to create the full system. Testing ensures that the components work together as expected when the system is tested as a whole. For example, in the same example that I used before, you might test the entire shopping cart system, including adding items, calculating totals, and completing the checkout process to ensure a smooth interaction between all parts. Each of these steps plays an essential role in finding and fixing issues early in the development process. Before moving to the next stage of testing, I want to give you some details about each of these development testing stages. I believe you now have a clear understanding of what unit testing is. It is the process of testing individual components in isolation to make sure they work as expected. This includes using defect testing to check that the function or unit performs correctly under different conditions. Of course, it is important to note that testing can only show the presence of errors, not prove that there are no errors at all. Whenever possible, unit testing should be automated so that tests can run and be checked without any manual efforts. So unit testing typically has three main parts. The first one is the setup. This is where you prepare the system for the test by setting up the inputs and defining the expected outputs. Then a call. Here you call or execute the object or method that you want to test. And finally, assertion, when you compare the actual result of the call with the expected result. If they match, the test is successful. If they don't, the test has failed. Automation and following this structure make unit testing more efficient and reliable. In this week assignment, I have asked you to implement a function to calculate the slope of a line connecting 2 points given their Cartesian coordinates, and to design test cases for this function. If you can make the testing automated, that would be great. It might require a little bit of research online, but don't worry, it's not too complicated. This leads us to two main types of unit test cases. The first type mirrors the program's typical operation. These test cases demonstrate that the component works as expected under normal conditions. The second type is based on testing experience, focusing on areas where common problems tend to occur. These tests use abnormal or unexpected inputs to ensure the components handle them correctly without crashing or producing incorrect results. Now let's talk about testing strategies. In general, we have two testing strategies. The first one is partition testing. This strategy involves identifying groups of inputs that share common characteristics and are processed in the same way. For example, if you are testing a function for calculating discount, you might divide inputs into groups like the valid discount rates, invalid rates, and edge cases. You then choose test cases from within each group to ensure all scenarios are covered. In the guideline-based testing, this strategy uses testing guidelines, which are based on past experience to choose test cases. These guidelines reflect common mistakes developers make when building components. For example, testing how a function handles null values, or extremely large inputs, or unexpected data types. This figure illustrates the partition testing strategy. On the left side, we have the input equivalent partitions. These represent groups of inputs that share similar characteristics and are expected to be processed in the same way by the system. For example, if you are testing a grading system, one partition could include all scores between 90 and 100, which corresponding to an A grade. And you will have different groups based on the different grades that we have in this grading system. The system processes these inputs and produces outputs, as shown in the right side of the figure. Here we have output partitions, which represent groups of possible outputs. Each output partition corresponding to certain input partitions. And the goal is to ensure that the system correctly maps inputs to their expected outputs. By selecting a few representative test cases from each input partition, we can effectively test the system's behavior without needing to test every possible input. This approach reduces the number of test cases while ensuring a comprehensive coverage of the system's functionality. In the guideline-based testing strategy, as I mentioned before, it targets common mistakes made by programmers, especially with edge cases and boundaries inputs. For example, examine sequence with just one value to ensure the system handles the smallest non-empty sequence correctly. Since developers often anticipate multiple values in sequences, a program might filter with only one value. Test with various sequence lengths, including very short and very long sequence to check for unexpected behavior. Make sure to test sequences that touch the beginning, middle, and end of partition, as this can help detect issues related to boundary conditions. Let's say in a grading system, 90% should be considered as A or B. Include tests for sequence of zero length, as empty input often cause errors if not handled in a proper way. Choose inputs that will generate all possible error messages to verify that error handling works as intended. Repeat the same input or sequence multiple times to check for consistency and ensure the system doesn't fail under repetitive conditions. Force invalid outputs to be generated by using unexpected inputs or triggering unusual condition. Lastly, test for extreme computation results, such as values that are too large or too small, to ensure the system doesn't crash or produce incorrect outputs. Now that we are familiar with unit testing, let's move to combining these smaller units into larger components. While we have ensured that each individual unit works correctly, now issues can arise during integration, particularly in how these units interact with each other through their interfaces. The key question here is, what are the different types of unit interfaces? The first one is parameter interface. In this type, data are passed between components. For example, methods or function often use parameters interface to exchange information when a method is called. So I have a function, let's say it will calculate the square, and I want to use it for certain reason in another function. So I will call the square function, and I will pass the parameter, which is the data that I want to be squared. Shared memory interfaces. Here components are sharing a common memory segment. One component writes data into this memory and another component retrieves it later. This type of interfaces is often seen in embedded systems, such as when sensor data is stored in shared memory and processed by other components. Procedural interface, which encapsulate procedures or function within a component that other components can call. This is common in object and reusable components, where one component invokes a method or function from another to perform a task. Like when we have a list data structure and we have encapsulated in this data structure a function to do sorting, for example. And finally, message passing interfaces. Here, a component sends a message to another component to request a service. The second component responds with a message containing the result of the service. This type of interface is often used in object-oriented and client-server systems, like when a web server sends a response to a client request. For example, think of weather application. When you open the application, it sends a message or a request to a weather server asking for the forecast for your location. The server processes the request and sends back a message, which is the response, with the weather information, which the application then will display for you. After we understand the types of interfaces, let's explore the errors that commonly happen with them. These common issues can be grouped into three main types. The first type is interface misuse. This happens when a component uses another component's interface incorrectly. For example, passing the wrong type or number of parameters or sending them in the wrong order. The second type is interface misunderstanding. This happens when a component misinterprets how another component works. For example, a binary search function might fail if it is given an unsorted array because it expects the data to be sorted. And finally, timing errors. These are common in real-time systems where components share memory or exchange messages. Timing issues arise when one component produces data faster or slower than the other expects. And to solve this problem, most probably you'll need something similar to a buffer. Now let's look at some interface testing guidelines to address these errors. For interfaces using pointers, always test with null pointers to see how the system will handle them. For procedural interfaces, create tests designed to fail. This helps identify misunderstanding in how the interface is supposed to work. In message passing systems, stress test the interface by sending an excessive number of messages to identify timing issues. And finally, for shared memory systems, test different activation orders of the components to uncover hidden assumptions about data production and data consumption. By following these guidelines, we can identify and address errors that might happen with interfaces during the component testing. The final testing activity in unit testing is system testing. This is where we integrate all the components together to create a working version of the system, and then test the entire integrated system as a whole. The main focus of system testing is to ensure that the components interact with each other correctly. It checks that the components are compatible, that they transfer the correct data at the right time across their interfaces, and that they work together as intended. Another important aspect of system testing is verifying the overall behavior of the system. This refers to how the system functions as a whole once all components are integrated. This behavior might not be obvious from testing the component individually, so system testing is important to ensure that the entire system works as expected. Now that we are done with the last test in the unit testing, let's move on the next phase, which is release testing. Release testing is an important phase that evaluates a specific version of the system intended for external users. The main goal of release testing is to provide assurance to the system suppliers that it meets the specified standards or functionality. It's related to its not just its functionality, but also for performance and for reliability too. This testing typically uses a black box approach, focusing on the system's inputs and outputs, without considering its internal working. This is why some people used to call it functional testing. It is common for people to confuse between release testing and system testing because they appear similar. To clarify, release testing is actually a subset of system testing with distinct differences. For example, release testing is conducted by an independent team separate from the development team, and this adds an unbiased layer for validation to ensure the system is ready for real use. Another thing that is that while system testing focuses on finding bugs, which can consider the defect testing, release testing ensures the system meets meets its requirements and is ready for external use, which make it more validation testing oriented. Release testing incorporates several types of testing to ensure the system is fully ready for deployment. First, we have requirements-based testing. This testing ensures that the system meets all its requirements. Next is scenario testing. This focuses on real-world workflow to see how the system behaves under typical user scenarios. Lastly, we have performance testing, which assesses the system's ability to handle expected workloads and perform reliably under normal and peak conditions. Together, these testing types provide a thorough evaluation of the system, ensuring it's functional, reliable, and ready for users before release. In the following slides, I will show you different real-world examples for these tests. I will start with example for the requirements-based testing. Let's consider the requirements for a library management system related to overdue book notifications. If a book become overdue, the system should automatically send an email notification to the borrower. If the borrower fails to return the book within 14 days after the due date, a fine should be applied to their account. To validate this requirement, several tests could be conducted. For example, borrow a book and return it before the due date to ensure no notifications are sent or fines applied. Borrow a book and let it become overdue, and verify that the system sends an email notification. Borrow a book, let it remain overdue for 14 days, and check it if a fine is added to the borrower's accounts or not. And finally, simulate multiple overdue books and confirm the system sends individual notifications and calculates fines correctly. Now let's look at an example of scenario testing using the same previous library management system. Here is the scenario. A user borrows 3 books with different due dates. We first verify that the system accurately records the borrow dates and calculates the due dates for each book. Next, the user returns the books. One book before the due date, here we confirm no notification or fines are issued. One book on the due date, again, we check that no notification or fines are triggered. One book after the due date, we verify that the system sends an overdue notification and applies the appropriate fine. The user then renews one of the books before its due date. We ensure that the system extends the due date and doesn't send any overdue notification. And finally, the user logs into their accounts to pay the fine for the overdue book. We check that the system updates the account balance correctly and removes the fine. This example demonstrates how scenario testing validates the system's behavior in realistic situations, ensuring it handles a sequence of user actions as expected. Using the same system to give you an example of performance testing, performance testing ensures that the system performs efficiently and reliably under different conditions. Here are some examples. Simulate high user traffic by testing the system with 1,000 users logging in simultaneously to check if it can handle the load without slowing down or crashing. Stress testing during peak hours by simulating user borrowing and returning books, renewing loans, paying fines all at once to see if the system maintains its performance under this heavy usage or not. Database query performance by running tests to check how quickly the system retrieves book information when searching a catalog with 1 million entries. Finally, notification latency. Overdue notification should be sent to user without significant delay. Performance testing measures the time it takes for these notifications to ensure they are delivered promptly. The last test I have for you today in the verification and validation process is user testing. This is a critical stage where real users or customers provide feedback on the system through testing. Their input help identify any issues or improvement needed before the final release. Let's explore the three main types of user testing. The first one is alpha testing. This is conducted in-house by the development team, but involves selected users or customer representatives. For example, a library management system could have library staff test features like borrowing books or sending overdue notification to ensure that the system meets their needs. Then we will have beta testing. In beta testing, the system is released to a limited group of external users in a real-world environment. These users try the system and report any issues they encounter. For example, a library might invite a small group of patrons to use the new systems and provide feedback on usability and performance. Another example that I believe almost all of you are familiar with from gaming. In gaming, beta testing involves releasing the game to a limited group of external players to test it in a real-world settings. These testers provide feedback on gameplay, performance, and report bugs. And finally, acceptance testing. This is performed by the customer to determine whether the system meets their requirements and is ready for deployment or not. Using our library example, the library management could test whether all workflow like login, searching for book, and issue finding align with their expectations. That's all the material I wanted to cover with you today. To wrap things up, let's go through a review question to put some of what we have learned into practice. The questions that I have for you today is related to a banking system. You are a software tester for Banky. This is the name of the software or the name of the company. A company that has recently developed a mobile banking application. The application designed to handle regular banking tasks has a primary feature for transferring funds between accounts. The application mandates that users can only transfer amounts between $1 and 1,000 in a single transaction. So you cannot do transfer less than $1 or more than 1,000. The application also includes features allowing users to check their balance, transfer fund with a pre-transaction limit set between 1 to 1,000. This is what we mentioned earlier. Pay bills, and finally, deposit checks using their phone's cameras. The first question about test case creation. Using the defined range for fund transfer, which is from $1 to 1,000, list down at least 5 test cases for the transfer funds between accounts feature. Detail the test case name, input, expected output, and any prerequisites. Let's start first by listing the necessary details for the test cases. The test case name, input, expected output, and any prerequisites needed to conduct the test. The first test case I believe all of us would want to test is a regular money transfer. This involves transferring any amount less than 1,000 and greater than $1 to be considered as a valid transaction. I will name this transaction or this test case transfer valid amount. For the input, I choose a valid amount, for example, 500 bucks, and will transfer this amount from account 1 to account 2. The expected output should be 500 is conducted from the first account and 500 added to the second account. Let's think together about the prerequisites. What is the needed prerequisites? If you think that there is no prerequisites needed, it's a problem because there's a lot of prerequisites here. For example, we need to make sure that both accounts exist. And the second prerequisite is to make sure that the first account has a balance greater than or equal 500 to be able to do this transaction in a correct way. Now let's discuss the second test case. This time I wanted to test the boundaries to ensure the system handles edge cases correctly. I will name this test case transfer valid amount at border. For the input, I will use the boundary values, transferring either $1 or $1,000 from account 1 to account 2. The expected output is that the system will correctly deduct the transferred amount, either $1 or $1,000, depending on how much you transferred, from the first account and add it to the second account. The prerequisites for this test case are the same as the previous one. Both account exists and account 1 must have a balance greater than or equal to the transferred amount. This test ensures that the system accurately processes transactions at the lower and upper limits of the valid amount. Testing these boundaries is critical to catching potential edge case issues. Now let's move into the testing an invalid transfer amount. I will name this test case transfer invalid amount. For the input, I will use value greater than 1,000 to transfer from account 1 to account 2, let's say $2,000. The expected output should be an error message indicating that the transferred amount exceeds the valid limit for a single transaction. And of course, the prerequisite for this test should be that both accounts exist and account 1 must have a balance greater than 2,000. This ensures that the error occurs due to exceeding the transfer limit and not because of insufficient funds. This test case verifies that the system correctly handles and reports errors for transactions that exceed the allowed transfer limits. It ensures robust validation of input constraints. In the fourth test case, we will test transferring a valid amount from an account with insufficient funds. I will name this test case transfer overdrawn. For the input, I will use a valid transfer amount such as $600 from account 1 to account 2, and the expected output should be an error message stating insufficient funds. Of course, the prerequisite for this message to appear is that both accounts must exist and that account 1 must have a balance less than $600. This test case ensures that the system correctly identifies and prevents transactions when there are not enough funds in the source account, helping maintain accuracy and reliability in financial transactions. For the fifth test case, we will test transferring a negative amount. I will name this test case transfer negative amount. The input will be a negative value such as transferring negative $50 from account 1 to account 2. The expected output should be an error message like amount must be positive or cannot transfer negative amount. And the only prerequisite here for this test is the existence of both accounts. This test ensures that the system properly validates input and prevents invalid transaction involving negative amounts, helping maintain logical and secure operations. The last test case we will cover is transferring money from an account to itself. I will name this test case transfer to the same account. For the input, we will try transferring, let's say, $50 from account 1 back to account 1. The expected output should be an error message stating cannot transfer to the same account. And the only prerequisite needed here is the existence of the account 1. Of course, there are many other potential test cases, such as attempting to transfer from an existing account to a non-existent account. I encourage you to think about other test cases and come up with a logical rationale for them, just like we have done here, testing a wide range of scenarios, ensuring that the system can handle unexpected and edge case situations effectively. The second question I have here is about the testing types. Describe and justify the significance of the following types of testing for the Banky mobile banking application. Let's start with unit testing. Unit testing is critical for validating the smallest component or individual units of the application. While this is important for any software, it is especially significant for a banking application like Banky. For instances, ensuring that computations such as balance update or fund transfer are handled correctly on a micro level is essential to prevent financial inconsistencies. Even the smallest error in the calculations or logic could lead to a major trust issues with users or legal complications. Unit testing helps catch these issues early in the development process, making it a foundational part of delivering a reliable and accurate mobile banking application. Now let's move on to integration testing. Integration testing verifies that different units of the application work together seamlessly. While unit testing focuses on individual components, integration testing ensures these components interact correctly when combined. This is especially important for a banking application, where many functionalities depend on multiple units working together. For example, when a user makes a fund transfer, the system needs to deduct the amount from the sender account, add the same amount to the recipient account, update transaction records, and notify the users of the transaction status. So each of these actions involve different components, and integration testing ensures they all work together smoothly to provide a flawless user experience. Now let's discuss system testing significance for mobile banking application. System testing takes a holistic approach to ensure that the entire application meets its overall requirements. Unlike unit or integration testing, which focus on smaller part of the system, system testing evaluates the application as a cohesive unit. For a banking application like Banky, this means testing the complete workflow from end to end. For example, a user might log in, check their balance, transfer funds, and view transaction history. System testing ensures that all those processes work together seamlessly and meet the functional performance and reliability expectations. Finally, let's talk about acceptance testing. Acceptance testing is all about ensuring user satisfaction and system usability. It's the final stage of testing where the focus shifts to the end user experience. For a banking application, this type of testing is especially important. Users need to trust the application to handle their sensitive financial transactions securely, and they also need to find it intuitive and easy to use. For example, features like checking balance, transferring fund, or viewing transaction history should be straightforward and function without any confusion or errors. Ultimately, acceptance testing validates that the system meets the customer's needs and expectations. It's a key factor in the application success because a positive user experience directly impacts adoption, retention, and the trust in the application. This stage ensures that when the application is released, it's ready to provide a smooth and reliable experience for its users. Now let's discuss the next question about test automation. Delve into the pros and cons of integrating test automation for banking mobile banking application, especially focusing on fund transfer functionality. Let's start with the advantages. The first thing, of course, is speed. Test automation is significantly faster than manual testing. This allows frequent checks even after small code changes, ensuring the system remains robust. Second, consistency. As automated testing ensures the same areas are consistently tested every time, reducing the risk of human error or oversight. And finally, increased coverage. Because automation allows for testing a wider range of scenarios in shorter time. For example, testing various fund transfer amount or multiple simultaneous transactions. For the disadvantage, the first thing, of course, is the initial setup costs and the maintenance overhead. Automated tests can become outdated when the application evolves, requiring regular updates to maintain relevance. And finally, it cannot replace human intuition. While automation is efficient, it cannot detect usability issues or understand user behavior like human tester. For example, it might miss cases where the interface is confusing for users. In summary, test automation is a powerful tool for ensuring the reliability of critical features like fund transfer, but it should complement, not completely replace, manual testing efforts. This balanced approach ensures both efficiency and thoroughness. The last question for today's video is about non-functional testing. Identify the importance of two non-functional testing types that you deem highly relevant for a mobile banking application like banking. Let's focus on two critical types of non-functional testing: performance testing and security testing. Performance testing ensures the application remains responsive, stable, and scalable under various conditions. This is especially vital for a banking application where high traffic is expected during events such as payday or promotions. Imagine users trying to log in or transfer funds during these peak times. Slowdowns or crashes would not only disrupt the transactions, but also damage user trust. Performance testing help identify and address these issues before they affect real users. Security testing evaluates the application for vulnerabilities, ensuring sensitive user data and financial transactions are protected. For a banking application, security is important. A security breach could lead to money being stolen, legal problems, and serious damage to the application reputations. This type of testing looks for issues like unauthorized access, weak data protection, and insecure communication to keep users safe and maintain their trust. Finally, both of these non-functional testing types are critical for a mobile banking application to ensure it delivers a reliable, secure, and smooth experience for its users. That's all I have for you today. Thank you so much for watching the video. I hope it was helpful and give you a clear understanding of one of the most important activities in the software development process, which is verification and validation. Today, we learned the difference between the terms validation and verification, and we also covered the different testing stages, including development testing, release testing, and finally unit testing. See you in the next video. Bye bye.